Um, right, for a solar eclipse, the Earth is in the moon shadow. And so in a lunar eclipse, the moon is getting blocked out. In a solar eclipse, the sun is getting blocked out as viewed from Earth. And so that's why they're called what they're called. In this case, everybody gets to see it who can see the moon. In this case, you only get to see a total solar eclipse if you're under the tiny little area that that shadow covers. And that's why, a bunch of us drove to the north in 2017 to get to the path of the eclipse. And the one that's happening in 2024, which is less than 4 years from now, will be, we'll have to travel south to get to that. It'll cross southeastern Oklahoma and go through South Texas. There are not very many more in this century. I think there's one in 2045, and then in 2061 or something like that. In your lifetime, there might be 3 more decent ones. This one in 2024 is probably going to be the best one for the rest of the century. And I've said this before, having nothing to do with science, it's totally worth seeing. It's a life event. It's totally worth going and seeing it. Skipping a day of work or 2 days of work, driving into the path of the eclipse so you can see that. You will understand why, wars stopped, kings were overthrown, all sorts of crazy things happen when the sun gets blocked out. It's a life experience. It's not just a science thing. So that's the short definition. You should look at the pictures in your book on what a solar eclipse looks like, what the positions of the objects are, and what the for both a solar and a lunar eclipse. So some language for this is the umbra is the darkest part of the shadow. If you're in the umbra, you can't see any of the light source. And so if you just draw like if this is the sun and this is the earth, am I off my screen? I am just about. I wonder if I can I make this any wider? Hey, what if I do this? Bam, that worked. Old school. And this is the moon, right? Then, if you're inside, if you're in here, you can't see the top of the sun and you can't see the bottom of the sun. Let me draw an Earth that's a little closer to that. All right, so this is the Earth and this is the moon. Anytime you're in here, in order to see the top of the sun, you have to be above this line. In order to see the bottom of the sun, you have to be below this line. And so if you're in here, you can't see the top or the bottom. So this is the umbra. Right. And you'll see a diagram in your book. I'll use a different color for this. But so if I'm up here, I can see at least some of the top of the moon, top of the sun. And so if I was up here somewhere, I could see maybe that much of the sun, the stuff above that, but not below. And so you can say, look, if I'm in this region, I can see part of the sun. And so this is called the penumbra. I'm probably off the screen. So in the umbra, you can see none of the light source. In the penumbra, you can see part of the light source. So in a partial solar eclipse, you're in the penumbra. You see part of the sun, you're over in this region, right? Same thing with a partial lunar eclipse. Part of the moon passes into the umbra, part of it passes into the penumbra. Okay. So that's the umbra and the penumbra. So it's a polar. So I'm going to skip down to the line of nodes. Let me just see if I can pull up a picture for this real fast. Maybe not so fast. So I'm just going to work on that. I'm going to try it. I'll go back up to that in a second. No. I lost it. Here we go. So you can see that the plane of the Earth's orbit around the sun is, which we call the ecliptic, is not the same as the plane of the moon's orbit around the Earth. Here's the Earth's orbit around the sun, this little light, this larger light-colored circle, and then this is the moon's orbit around the Earth, and you can see they're tilted. The line where they cross, where the moon's orbit around the Earth crosses the Earth's orbit around the sun, is called the line of nodes. And in order for you to get an eclipse, that line of nodes has to be pointing towards the sun, because that's the only time the moon can be in the same plane as the sun and the Earth, or at least in the ecliptic, to get right between them. And so you can see here in the bottom of the screen or on the top of the screen are the only places where you can have that. And so the Earth has to be in that position in its orbit, and then to get an eclipse, the moon has to be in the corresponding one of these two positions. If it's outside the sun, you get a lunar eclipse. If it's inside, if it's on the sun side of the Earth, you get a solar eclipse, and it's on the outside of the Earth, away from the sun, you get a lunar eclipse. And you can see, since the Earth has a bigger shadow, all of the moon is in the Earth's shadow, but for a solar eclipse, all of the Earth is not in the moon's shadow. And so okay. More just vocabulary stuff. So the thing we call a mean solar day, which is kind of our 24-hour day, is sort of the average time between noon and noon, where noon is defined as when the sun crosses the meridian, right? When the sun is right at the center of your sky. If you measured that every day for a year, when your shadow points, when a shadow is a vertical stick points exactly north, that's local noon. If you measure the noon to noon times, it'll vary over the course of the year because the Earth has an elliptical orbit, and sometimes it's moving a little faster because it's closer to the sun. Sometimes it's moving a little farther away. And so our mean solar day is the noon to noon time. A sidereal day a sidereal day is the time it takes the Earth to just do one complete rotation on its axis, sort of turning all the way around one time relative to the fixed stars. The stars are not fixed, but they're so far away that they appear fixed because even though they're moving fairly fast, it's like it's playing this up in the sky really, really high. It looks like it's moving really slow. The stars are so far away that that we might as well just treat them as stationary. So if I draw a picture of this, right, and I know I did this in class, but that's the Earth's orbit. Here's the sun. Here's us on the Earth. Right, so since the sun's directly over my head, I was trying to make that directly over my head. Right, that means it's noon where I am. If I let the Earth rotate one time just on its axis, then because it's also orbiting the sun, it's now over here. And so if I just wait for it to rotate one time on its axis, this would be my head pointing straight up. This would be my head pointing straight up relative to the fixed stars. This would be a sidereal day. But we wouldn't call this a solar day, because in a solar day, I have to wait till my head's pointing at the sun, and that takes a little longer. The Earth's got to turn a little farther. I'll draw it over here, even though it's a wild exaggeration. Once the Earth is turned a little farther, now my head is pointed back at the sun again, and so this is noon. So a solar day is longer than a sidereal day, because the Earth has to, this person goes all the way around here and comes back vertical here, and then it's got to turn a little more to get back where their head is pointed at the sun at noon. So this is the sometimes called a solar day, a synodic day. So that's the difference between those two. There are all kinds of stuff that makes this complicated, right? The Earth's orbit isn't circular, so sometimes the Earth is moving faster than here, sometimes it's moving a little slower. So it goes a little farther. That means it has to rotate a little further to get back to noon. So the length of a day is a hard thing to exactly understand without really understanding the geometry. That's mean solar day, a sidereal day. And so it's the same thing with the moon. Sidereal period. So I could use the exact same picture, and instead of this, I could have the moon here. So once again, here's the sun, just like in the previous picture. You should always draw your circle and then draw your center. Good. So here's the Earth, right? And now I've got to draw the moon orbiting the Earth, right? And so first of all, if I say the moon is here, what's the phase of the moon in that position? Can anybody shout out to me? So you should definitely know all the phases and where they correspond to. So hopefully you can
Is it a new moon?
What's that?
Is it a new moon?
Yes, ma'am. It is. Great. So perfect. So you should know that this side of the moon is lit, and so this is the dark side. And when you see the dark side of the moon, I don't know if you listen to Pink Floyd, but if you don't, you should. The Dark Side of the Moon is one of their albums. It's probably the best rock album of all time. So that's the dark side of the moon, and so the phase is new. Right, if the moon was over here, we'd be seeing all of the lit side, and this would be full. And so on first quarter, third quarter, it's going around like this. Right. So if we just wanted to know, so here's the Earth later. Right, here's the Earth later. If I just want one complete orbit of the Earth, then I have this. Right, the moon would be up here, right? Because it's going around one time, it's back to on top. We're going around one time back to on top. But that's not what we call, so this would be a sidereal month, or the sidereal period. It's the time, it's one orbit relative to the fixed stars, not necessarily relative to the sun, relative to stuff that's way far away, right? A synodic period would be till you get back to a full moon, a new moon. Oops, and I completely goofed that up, didn't I? So here, there, like that. And so if I wait till it gets all the way around to here again, this is the synodic period. Technically, this one takes longer, right? Because once it was rotated to here, it's got to take longer to come all the way back around to this position. And so what I drew is a little bit awkward. But so a synodic period for the moon, it's like 29.5 days, and the sidereal period is like, it's about 27. I think this is 27.5 or something like that. This is about 29 something, maybe 29 and a third. I can't remember. It's something like that. It takes a couple more days for it to get back to. Once again, just like with the date, the time for a day on Earth, because the Earth is moving faster at different periods of its orbit, and the moon is orbiting the Earth, the time, the synodic and sidereal periods vary a little bit over the course of the year. The synodic period does. The sidereal period doesn't change, but the synodic period does. And so, so we talk about an average. This, by the way, would also be the average time between full moons, or the average time between first quarter moons, or any of that, right? Because it's just whatever phase you want to pick. You know, the time between this one and the next full one, on average, is going to be the same as the time between the successive new moons and so on. And so that's the synodic period. What are seasons caused by?
The tilt of the Earth's axis.
Right. So if your hemisphere, and by hemisphere, I mean, north or south, if you live in the northern hemisphere, like we all do, when it's tilted towards the sun, we're kind of in summer. It's a little more complicated than that, but that's basically it. And then when we're tilted away from the sun, it's winter. Technically, when we're tilted most toward the sun, that's the summer solstice, the beginning of summer. And we're tilted most away from the summer, that's the winter solstice, the beginning of winter. And so halfway between those, we're kind of tilted laterally to the sun, and that's either the spring or the autumn equinoxes. All right. Is there something else I wanted to say? So tides are caused by the moon mostly, and by the sun, about half of the moon's effect. And so you get a high tide when the moon is overhead or underfoot. I'm just going to pull up and write some and show you some of these things that I wrote so you can see. So the sidereal period, one orbit relative to the fixed stars. The synodic period is the average time between new moons. Seasons are caused by the tilt of the Earth's axis. So tides are caused by the moon mostly, and by the sun, about half the moon's effect. High tides when the moon is directly overhead or underfoot. Let me just see if I can pull that back up here for a second. So when you're over here, you get a high tide, or over here. Remember, the moon is this way. When you're 90 degrees to that, you get a low tide. So in this picture, the low tides are the top and the bottom of the moon, of the Earth, and the high tides are the left and right. You don't get any bigger high tide when you're on the close side than you do a high tide when you're on the far side. The moon just stretches the Earth in that direction on both sides. Well, get there. Here's just a nice picture of what happens when the tide goes out. Coast people problems, I guess. And so then here are some special cases of where the sun and the moon make a straight line, or the sun and the moon make 90 degrees. When they make a straight line, you get extra high tides and extra low tides. Those are called spring tides. So spring tides are when the sun and moon's poles reinforce each other. And they can either both be on the same side or on either side. And so you get a spring tide when they just make Earth, Moon, and Sun make a straight line. And you get a neap tide where the high tides are low and the low tides are a little high. That's when the Sun, Moon, and Earth make a 90-degree angle. Here were just a couple of nice pictures of the eclipse. I lost it. That's just a convenient picture to talk about the mean solar day. You have to rotate a little bit farther. Let me get back down to here though. So this is a nice set of pictures just out of your textbook. It shows where the umbra is, right? And so if you're standing on the moon, looking at the Earth, this picture 1 over here is what you would see from the moon. If you were in position 2, this is what you would see. You would see a lot of the Earth and a little bit of the Sun wrapped around it. That's position 2. Position 3, you're almost out of the penumbra, and so you see the Sun partially blocked, but not quite, not all that much. And finally, if you're in position 4, you're far enough away that the Earth looks smaller than the Sun, and so you get what's called an annular eclipse. And so you can get all of those things, just depending on which position you're in. There's the umbra, and outside here, these are the penumbra, where you can see at least part of the Sun. So here's a nice picture of the eclipse path, right? With the moon between the Earth and the Sun, and you can sort of see that triangular cone of shadow hits the Earth before it goes to a point. And so as the Earth turns on its axis and these guys are all moving, that shadow kind of glides across the Earth somewhere. And if it happens to pass over your head, you get to see a solar eclipse, which looks like that. Similar with the lunar eclipse, except more people get to see it, and you can sort of see that if you just happen to be on the dark side of the Earth, the moon side, then you can be standing anywhere there and you get to see the moon as it was. This was the one from 2017 that we went to see. The other one, the new one's going to be tracking across here somewhere. I think it tracks from South Texas up through maybe New York. Can't remember if you could go back. All right, that's chapter 4. I'm not moving very fast. Okay, so chapter 5. Types of spectra. So we talked about we looked at some of these things, right? So a continuous spectrum is just a full rainbow of colors. It's what we saw when we used that diffraction grating and looked at a light bulb filament. That was just, you saw all the colors of the rainbow. And so it's just due to a hot, dense object. An atomic So an atomic or an emission spectrum is what you get when you heat a gas, and that was the one we did where you saw individual colored lines, discrete or specific lines of color, characteristic of the properties of the heated element. So every element has its own fingerprint. And so if you have a dense object, you get a continuous spectrum. If you have an atomic gas, you get what's called an emission or atomic spectrum. And that's a series of colored lines. So full rainbow, individual colored lines. So an absorption spectrum is when you have a cool gas. So you take this gas, whatever it is, neon or whatever, make it cool and put it between you and something that would be giving you a rainbow. And so let me see if I can pull this one up. Oh, I kind of goofed that up. Let me try this. Okay, so these are our spectra. We have a continuous spectrum, which is the full rainbow. It's due to a hot, dense object. It's continuous, it's what we saw. Here's the atomic spectrum. It's discrete, specific lines of color, characteristic of the properties of the heated element. So we saw a different one for hydrogen, a set of colored lines, than for helium or neon. Then here's the absorption spectrum. And so when you take a cool gas like our atmosphere and put it between you and a hot, dense object like the sun, you get dark lines superimposed on the front of a continuous spectrum. Let me just see if I can pull that up. Talk about that for a second. Maybe. There it is. So this is a rainbow that's been kind of chopped up and made to look the way it does. But that should, every one of those lines going across there should be stretched out. So this should be one huge, long, single horizontal band that goes from blue all the way to red. But you can see all the dark lines superimposed there. And those are the fingerprints of all of the gases that are between us and the sun. All those dark lines are. And that's what you're seeing. We've got cool gas that's between us and the sun. And so you're seeing discrete absorption lines laid out, superimposed on top of that continuous spectrum. And so those lines tell us what gases are between us and the sun. And we can do it for all kinds of stars. And so we can tell what gases are surrounding different stars, and what gases are in our atmosphere. There are all kinds of tricks we can do. We can look at gases emitted by like Mars, because Mars is just reflecting sunlight. And so we can tell what's in Mars's atmosphere by looking at the light coming off of Mars, knowing that it's coming from the sun, so it should be a continuous spectrum. And we can see what Mars's atmosphere filters out. And so it's how we tell the composition of the atmosphere of other planets and other objects. Okay. Let me go back to this. Eesh. here it is. Here's the continuous spectrum from the sun with the dark bands in front of it. All right, stop that. Okay. A little bit about spectra. Components of an atom are electron, proton, neutron. These guys live in the nucleus. This guy has charge -1. This guy has charge +1. This guy is neutral. An ion is an atom with an unequal number of electrons and protons. So it's either got more electrons than protons or more protons than electrons. If it's got more electrons, it's called a negative ion. If it's got more protons, it's called a positive ion. The atomic number is the number of protons. This identifies the element, whether it's hydrogen, which has 1, or helium, which is 2, which is lithium, which has 3, or boron, which is 4, beryllium, which is 4, boron, which has 5. I had to look at the periodic table. All right. The atomic mass is the number of protons plus neutrons. It's basically the mass of the object because the electrons are so light, they hardly matter. So an isotope is an atom with the same number of same atomic number as another atom, but a different atomic mass. In other words, same number of protons, different number of neutrons. And so those are called isotopes. Those come up a lot in sort of nuclear processes, radioactivity, stuff like that. All right. I think I'll stop there. I may just go on tomorrow. So we're not meeting class in class tomorrow. We're going to Zoom again because campus is closed for in-person tomorrow. And so we'll have the test whatever day we get back. If we get back on Wednesday, we'll have the test on Wednesday. If we get back on Thursday, we'll have the test on Thursday, and so on. All right, I'll hang around for a minute if you have any questions. Otherwise, see you guys tomorrow. I'll set up a Zoom again.
Appreciate you, Doctor.
Thank you, guys.
Mr. Trail,
Yes.
is the vocab, like, do we need to write the vocab out or is it going to be multiple choice?
The whole test is going to be multiple choice.
Okay, awesome. Thank you.
Yeah, if you can just sort out what the right answer is, you'll be good.
Awesome. Thank you.
Yeah, you bet.